Yeah, that we like to record these so others can watch them after the fact. So just keep that in mind. So yeah, it's my pleasure to have Rakesh Bobba today. He's an associate professor here at OSU. He got his Ph.D. from the University of Maryland in 2009, and then he joined as a research assistant professor at the University of Illinois, Urbana-Champaign, and did tons of diverse security work there. And in 2014, joined OSU. And yeah, as I said, he's done a lot of diverse work. So he's got a breadth of knowledge that's really amazing, and depth in certain areas as well. But I think of him as a jack of all trades in security. He's doing really interesting things in terms of increasing the educational programs here at OSU in security. Some of you may have heard about ORTSOC. If not, you can talk to him about that at some point. And just a lot of interesting research in distributed systems, cyber physical critical systems. I mean, these things are going to be headline news in the years to come. So we need people like Rakesh educating our students. And so yeah, he's going to talk about one of his many topics today, and yeah, I'm looking forward to it. So it's all yours, Rakesh.
Thank you, Alan. Appreciate it. Good morning, everyone. Thanks for joining. I know you have lots of other things to do probably, so I appreciate you taking the time to join this talk. So as Alan mentioned today, that I'll talk about one of the projects that we've been working on at OSU for a couple of years now, looking at usable and practical image privacy protection mechanisms. This is a joint work with many collaborators that I have included the pictures at the bottom. Most of them are were at OSU, but we have two collaborators from PSU, so I want to give a shout out to them, Wuchi Feng and Charles, the last two folks here. So let me dive in. Let's see, I need to figure, yeah. So Alan already gave a little bit of intro, so I won't dwell on here. I'm gonna move on. So in terms of my research space, I primarily work in networked and distributed system security, and it's a pretty broad area. So I have a couple of focus areas that I've been working on over the past few years. Cyber physical infrastructure security, so looking at security for power grids, manufacturing plants and so on. So one recent grant that we got, a couple of them are looking at security for UAS or unmanned aerial systems, and looking at risk assessment in nuclear plants and so on. I used to do a lot more in this, not as much anymore, looking at cloud computing security. So these look like side channel attacks in cloud environments where you're co-hosted with potentially unknown entities on the same hardware. And you all might have heard about these side channels, the famous ones being the Intel ones that came out on the speculative execution and so on recently. I also do a little bit in usable security and privacy, and that's the focus today of our talk. This space, we'll talk about usable privacy for images. The other big area I work on, there's a little bit of overlap between real-time systems and cyber physical, but they have distinct concerns, is looking at how to integrate security into systems that have time constraints, right? So just a quick flavor for what happens in this area. Let's say you want to integrate some security mechanisms. Let's, for the sake of it, say intrusion detection systems. These intrusion detection mechanisms have to coexist with real-time tasks that have deadlines that they need to meet. So you can't have a virus scanner or an intrusion task pop up and hog the CPU, causing the real-time tasks to not meet their deadlines, right? So we did a body of work starting 2013, 14, almost last 7 years, on how to schedule these security tasks in real-time systems so that they're effective, but they are not impacting the execution of the primary task of that system. So you can think about drones or autonomous vehicles and so on, right? So the first problem we looked at, as I talked, is integrating intrusion detection systems. The first work simply said, hey, we will execute them whenever there is an opportunity on the system. We called it opportunistic execution. Eventually, that was for single core. Typically, most real-time platforms were single core even then. They're slowly becoming multi-core. So a couple of years later, we extended that work to a multi-core environment. We also looked at, as I mentioned, I did some work on side channel prevention, cache-based side channel prevention in cloud-like environments. We brought those ideas into real-time systems, especially when you have multi-core and you're putting, in a multi-vendor model, you might be putting applications from different vendors onto your platform, and necessarily you don't trust all of them from a security perspective. So how do you do cache side channel defenses without impacting the real-time aspects of the system? So that was the focus of some of these works, and most recently we discovered a new side channel in a real-time scheduler, and we showed how to use that to launch other attacks. So this is just an overview of, just wanted to give you a flavor of an area that I work on. But today we are going to focus on usable security and privacy. Any security mechanism that we design, as you probably already appreciate, are only as good as how well they can be used, right? So it's important to design them such that it's easy for users to deploy or use them. So a problem instance we'll look in this space is, how do we design a security mechanism or a privacy mechanism for images that also has usability, so it's easier for end users or people to deploy it. So what's the problem that we're looking at? Billions of images are stored or shared using third-party services every year, right? I think there was an estimate of about 1 billion images a week shared through services like Facebook. And this is sharing, but we also typically tend to store our images in many services out there. Google Photos, Apple Photos are examples that came to mind. So how do we protect ourselves in such environments? Why do we actually use these services, right? Because they give you storage that's typically, it's cheap now, but still reliable storage is not easy to set up at home for most users. Convenient access, you can access from anywhere, you can share it with people, and you can organize and manage them, right? But the downside is typically providers tend to have access to these stored images. So it's a very usable solution today. It's easy to store, and you can snap a picture on your cell phone and immediately store it in the cloud. But the privacy is questionable, right? So why is this a concern? These are some old attacks. We've seen much newer ones, recent ones. I should probably talk about some newer ones, but we know that typically these third-party services do use user data for their own business model or for their own benefit, or sometimes to satisfy requests from third parties. This is showing that Facebook actually has face recognition capabilities, but using them without causing privacy issues is tricky. So they've been known to use that. Even if you have a good third-party provider that is benign and doesn't want to leverage your personal information, there's always the risk of hackers compromising those services. And we've heard about news articles where even Apple's iCloud got compromised, Dropbox got compromised, and people lost data, right? So these are just a few examples. The other thing that's coming up, or rather it's already here, is the emergence of machine learning or AI, right? They've become really efficient, really good. So recent research has shown that by just tracking images that people post on social network, Users' relationship status can be ascertained by detecting faces and seeing how close people are standing to each other, and so on, right? So face recognition is an important part of this pipeline, right? So here it's this is focused on celebrities, but you can do this for regular users. A new one, this was actually in the news a couple of days ago as well, is this Clearview API. Not sure if you heard about it. It's typically available for law enforcement, where people can take a picture of you and scan the entire publicly available images to recognize who you are, right? To identify who you are. I don't remember if it was the Canadian or the German courts decided that this is illegal. Recently, it was in the news. So, but in the US, I believe it's being used. So there's enough images probably of us online that if somebody wants, they can gather them in one place and learn a model to recognize us in future images, right? So these are some of the threats of sharing images without protecting them or storing them. So we have a two-part talk today. In the first part, I'm going to talk about something called thumbnail preserving encryption. Some of you on this call might have seen this before. We've demoed it for our IAB meeting in 2019. The second part looks at adversarial perturbations for privacy, specifically against CNNs, not against humans. For example, a third-party service provider employee could look at the image and recognize, but we don't want that to be scalable such that they recognize your images or you in images at a mass scale using CNNs. Okay, so let's dive into the first part: thumbnail preserving encryption. What does this mean? So a naive solution to deal with this image privacy problem would be to encrypt your image and store encrypted images in your third-party provider. There's a lot of encrypted file systems that you can use to do this. But the problem is, so when you go back to browse your albums online, instead of seeing this view on the left, you will see this view on the right, where most of the images are look like garbage, right? You can't distinguish between the images. I mean, here these are independent individual portraits, and you can put a name, and that's good enough. But think about wedding albums or birthday party albums. There are multiple people, multiple contexts and stuff. You can't capture all of that in the names and browse using names. It's not as easy as visually browsing through your albums. Okay, so that's one challenge with naively encrypting, is that it provides good privacy, but it's less usable, right? So we're trying to balance this. So in 2015, our colleagues from Portland State came up with this idea called thumbnail preserving encryption. And the idea is that, when you encrypt an image, so this is our colleague, it does leak some information, right? You can probably tell there is a person here, maybe not much more if you just saw the encrypted image, but it hides key details, but it does leak some information. And the idea is that it's leaking what we call a thumbnail, right? So what is a thumbnail? Just for those as a refresher, I'm checking to see if there are questions. Okay, so let's say this. This is a representation. This little squares are pixels in an image, right? So I could, for example, take an average of all these pixels and represent this entire block of pixels using just one pixel. So I'm taking a high resolution image and creating a low resolution image just for browsing purposes. This is what services like Google or Apple or even your own computer does when you're trying to browse through pictures on your images. You'll get these little thumbnails that you can look at, right? So it's sort of reducing the granularity and showing it. And this is what happens, right? So the idea was that what if I can maintain this average value during encryption, so that when they compute the average on the encrypted image, you'll get the same average as you would get on a unencrypted image, right? So that's preserving the thumbnail even though the image is encrypted. Okay, so we'll see an example. So the original scheme from 2015 was to say, okay, I'll take a block of pixels and I will simply permute them in a random way, so that it's the same set of pixels, but they're not in the same locations as they were before. So the sum or the average is preserved, but visually it's jumbled up, right? So this is basically what the result of that operation is. Every block, so this is a block of pixels that is kind of jumbled up or permuted, right? So this is a block of pixels that's permuted. So if there is no variation, you can see it leaks information, but otherwise it's pretty good at hiding information. The problem with this approach is, so yeah, this is how you expect it to look. This is the original image. That's the thumbnail version, so average down version. This is the encrypted image. You can see it hides the information pretty well, but the thumbnail looks the same. It's essentially the same, pixel by pixel. But the challenge with this approach was that it actually leaks the pixels that are in the image. So it's hiding, some visual detail, but the actual pixel values are leaked. So we wanted to do something, more secure, right? So this is what we call ideal thumbnail preserving encryption. And the idea is that we don't want to leak anything other than the average. So what do we mean by this? Let's say we have a block of pixels whose value adds up to some number X, right? If we preserve the sum, the insight is if we preserve the sum, we preserve the average too. So let's say we have a block of pixels in, somewhere in this image whose sum is X, right? We can conceive of a whole number of combinations of pixels whose sum will also be X, right? So there is, for just visual representation, I'm putting 4 out there. If there is a way for me to randomly pick one of these combinations and replace the original with this, then, and I can do this for every block in the image, then, if I call this encryption, the encrypted image will have the same sum in each block, but, the image will be totally different, right? So not only should I be able to do this efficiently, but I should be able to reverse it, right? So that's the idea of thumbnail preserving encryption. But it turns out that random selection is impractical, even for small block sizes. For example, even if I just have a 2 by 2 block, 4 pixels, right? There are 2 raised to the power of 17 combinations that for a given sum you can find. And even with just 16 pixels, the maximum number of combinations you could have ends up being 2 raised to the power of 83. And after some while, it's intractable, right? You can't compute this, right? You can't create all these sets and randomly pick one out of them, right? So it's not practical to do it this way. So what we came up with is what we call a substitution permutation based encryption. For those who are familiar with crypto, this is, these terms are used in traditional, ciphers have substitution and permutation operations. That's why we use those names. But it's much easier to understand. The idea is actually quite intuitive and simple. If I take 2 pixels, I'm going to substitute them with, 2 different pixels whose sum remains the same, right? So I can do this. Remember, for 4 pixels, it's difficult. Our intuition was with 2 pixels, it's easy, right? So for every pair of pixels, we do this substitution. And then we permute the pixels and we do the substitution again, and we permute and do the substitution again. So a good way to think about this is like 2 atoms that collide, exchange some mass, but the mass is preserved, right? And then they disperse, collide with some other atoms. Their mass is always preserved, but they, we don't lose mass, and the atoms kind of preserve the mass, right? So it's a made up scenario, but that's a good way to imagine this operation. So if you take a block of pixels, do some substitution, you do permutation, you get a new block of pixels, and you keep doing this process. And after some number of, we call this a round, after some number of rounds, you say, okay, that's good. I'm done, right? So then we'll end up, if we do this right, we'll end up with a situation where I have these images that I've uploaded encrypted. I'm showing the full cipher here, but these will be smaller size, but at least these are browsable. We do a usability study to show these are browsable. Okay, so I don't get into the details, but turns out they're browsable. Okay, so how do we know that this approach is secure, or how do we show that this is secure? Just a little bit of detail that I'm not getting into today is that to do these operations of substitution and permutation, we use the advanced encryption standard, the typical AES encryption, standard AES that NIST is proposed. We use that for substitution and permutation operations to keep them secure. So I'm going to skip over this detail. But the key question is, okay, if you think of these as atoms hitting each other and mixing up their mass, how many times do they need to go through this before the resulting image is, there is no way for somebody who doesn't have the key to reverse it back to the original image, right? Turns out the atoms analogy is also a good analogy, so that you can think of these atoms mixing with each other. They crash into each other, pop out as two different atoms that with the mass preserved, and how long does it take for it to look as if I've picked a uniformly random combination to begin with, right? So we can model this as a mixing process, right? As a Markov mixing process. And it turns out that the number of rounds required to get a uniform mixing, for a lack of a better word, is what's called the mixing time for a Markov chain, okay? So we model our encryption process as a Markov chain, and we end up this, fancy looking expression. Essentially, this omega is the number of possible combinations of block of pixels that add up to the same value. And this lambda star is the second eigenvalue for, if you're familiar with Markov chains, there is a transition matrix, probability transition matrix, that tells me if I start in this state, what is my probability of going to a different combination of pixels from there, right? So this is the second eigenvalue of that matrix. So we can compute the mixing time in theory, right? Turns out that even for block sizes of just 16 by 16 pixels, I can't really compute this lambda, because sigma is so large, I can't compute the probability transition matrix. But what we can do is, since lambda is going to be between 0 and 1, I can say, okay, assuming lambda is anywhere on this, what does my mixing time look like? And it turns out that, if I'm using a block size of 32 by 32 pixels, I'm somewhere around 1,000, roughly about 1,000 encryption rounds before I can get the ideal mixing. So this is an asymptotic result. We don't have, a concrete result that, okay, if you give me this block of pixels, I can tell you how many rounds of encryption or substitution permutation to apply, right? But this is where we are. We are looking for a better way to model this. So even though the scheme is fairly simple, the security proof turned out to be very challenging, okay? So we did, as I mentioned, evaluate the usability. So we took a bunch of scenes from the TV series Friends, selected users who are fans or familiar with the Friends series, gave them thumbnails. I'm blowing them up so they look horrible, but if I show them in the thumbnail size, they don't look too bad. And turns out that they have within 80% in terms of if I'm able to quantify usability for the original images as 1, I'm able to get to up to 0.8 or a little bit above that for these images, which is not bad at all. It takes a little bit longer for them to recognize these, but people are able to browse through and sort them with reasonable ease. Okay. So the thumbnails actually look like this. So it's not this jumbled up like this, but it's kind of reasonable. If you look from far, you can tell it's a person. And the key factor that makes this work is that there is a result in cognition research that if I was the person who took this image, or if I was the person who saw this image before, I can recognize those images at a much low resolution than a person who hasn't seen this image before or who hasn't taken this. So for the cloud photo storage browsing application, it's the image owner who's encrypting them, storing them. It's the image owner potentially looking at browsing through them. So that helps with the usability. And we actually don't want others who haven't seen these images before to be able to recognize the people. So that's something from that we leverage in this work. Okay, so this concludes my part one. I'm going to jump into a different scheme for image privacy next. But if there are any quick questions, I'll be happy to take them now. Okay, I'm not seeing any, so I'll keep going. So the part two, the thumbnail preserving encryption is actually quite nice scheme. It gives you cryptographic security proof. It also actually turns out we can attach some formal privacy notions to that. But you know, there is a trade-off between usability and the security. If I make the thumbnail too small, even it's hard for people who've seen the images before to recognize. If I make it a little bit larger, then machine learning algorithms or other humans might be able to recognize. So there is that trade-off. So in the next part, what we wanted to do is that let's not worry about humans, right? It's think about this, right? There are so many posts on Facebook or Twitter or something, and you want to remove certain posts that violate the policy. They can't keep up with the volume because humans looking at these things is not scalable. So we said, okay, Google or Facebook or any of these third-party service providers, humans sitting and looking through all images is not scalable unless they're targeting you specifically. So, but what's scalable is applying a machine learning algorithm to at scale recognize people in images, right? So we said, let's focus on just thwarting the scalable image recognition, right? So in this part, that's our focus, right? So for those of you who are not familiar with this term, CNNs, it's convolutional neural networks. They're designed for image classification tasks, object detection and recognition in images or videos, and they've proven to be accurate. I think in the last 10 years, they've gotten really, really good. This data is actually old for 1,000+ classes, which means there are 1,000 different people in the images. They can get up to 98 or more accuracy. So this is a visual representation of layers of a network. We don't need to dig into the details, but just a setup. They're really good at image recognition and classification. Okay, but recently, about 4 or 5 years ago, people discovered that these CNNs have vulnerabilities in the sense that here is a famous image from that paper. Let's say you give this image to a CNN, well-known, well-trained CNN, and it classifies this as a panda with 57.7% confidence. But if you just add a small noise, look at the scalar multiple here. So if you add this random looking junk with a very low weight, visually the image hasn't changed for a human being, but now the CNN thinks it's a gibbon with 99.3% confidence, or very high confidence, right? And so basically this is a specially designed addition to the image to fool the CNN. So this was using fast gradient attack that came out in 2014. But this just illustrates that CNNs can be tricked into making false classifications. So one of the things we ask is, can we leverage this for image privacy, where we add some specially crafted noise to our images before uploading them into the cloud, so that if this cloud provider that we are using turns out to be not so nice and wants to mine my images for information, it's not going to work that well for them. Okay. Turns out people tried this, right? So this was one of the first works. But the thing there is they assume that they know everything about the target CNN. But it's unlikely that I would know the target CNN of the details of the CNN of Facebook or Google. These are not publicly or Clearview API, right? Further, they have to learn one perturbation for every image, and we mentioned that you learn this. It's an expensive task, right? Learning this perturbation, right? It's not cheap. There's a second work that came later. It learns one perturbation per image, but it can fool unknown CNNs. It's called face-off. So they use the movie analogy there. So, but it didn't worry about reversibility. Once you add the perturbation, it cannot be reversed back. So you can't get a clean image back if you want, which is not great for image storage application. Okay. These are fairly recent, 2017, 2020. So what we wanted to do is that we wanted to do this in a more practical way. Of course, I can't assume that I know all the details about CNN that Google or Facebook or Apple or whoever providers might use. So I want to be able to launch a black box mechanism where I don't need to know anything about those CNNs. You want it to be low computational cost. You can't expect users to learn a perturbation on a large CNN with 1,000+ classes. It takes a lot of computational power, especially if you have to learn it for every image, right? And I don't want to. If I want to reverse the perturbation I applied, I have to store the perturbation, so I can, if I added it, I can, let's say, subtract it. But storing a perturbation per image is a storage burden. If I have that kind of storage, I might as well store the original images locally, right? Or even, yeah. So we want to make sure that the images are recoverable and that these perturbed images are recognizable by humans. So I can browse, I can share it with friends, and they can look through the stuff. Typically, recognizability is not a problem for adversarial perturbations because, as you saw the panda image, you can't see that there was a perturbation. But it does become an issue if you are trying to fool an unknown CNN because your perturbation weight has to increase. So you add more noise, basically. Okay. And we want to be able to work with existing platforms. I don't want support from a platform to be able to deploy this approach, right? So we've kind of came up with these practical requirements for a scheme to be able to work. And we proposed, I'm not going to get into all the details, but we proposed what's called a universal ensemble perturbation. So that what that means is when I'm trying to learn the perturbation locally, let's say I want to protect my images, I want to add a perturbation to them, I have to learn that. So I'm learning it locally using 3 CNNs, not one, multiple, right? That's an ensemble of CNNs, but these are really small CNNs, roughly 10 classes compared to, 1,000 classes potentially that, large. And we learn them at different resolutions of the image. And we also learn the perturbation not for a given image, but we learn it over a set of images so that it can be applied to any image, right? Let me move on. And there's a special way we add the perturbation so I can reverse it without too much loss, okay? So this is a visual representation of this. So I have 3 local CNNs I'm learning, and I'm learning them to learn a perturbation, and I'm learning it on not a single image, but a set of images, 200, right? I'm not going to go into all of the details here, but the idea is that this is the perturbation that I'm learning, and I want to minimize it, right? Such that the goal is that if I add this perturbation to any of these images and give it to any CNN, any target CNN, it should misclassify it. That's the goal, right? So it turns out we actually succeeded in learning such a perturbation. So this, is a perturbation for one set of 200 images. As you can see, it's visually it's just a bunch of rough surface, but turns out when I add it, again, we don't directly add it. We add it in a special way, but the key to remember is that this is the weight. So this is the perturbation and this is the weight, okay? So for different values of beta, the perturbation becomes stronger. So the higher the value of beta, the higher the perturbation. I just want you to remember this beta equals 3. Turns out this is a sweet spot where you can still recognize the image, but you can fool most CNNs with this image, with this beta value. Okay. And we can take the original image, add a perturbation, and original image, add a perturbation, and reverse it without too many artifacts. Okay, so it's a reversible process. We tried this. We evaluated this using both online models. Google Vision API and Clarify is a well-known face detection model, and a local model that we train, Deep Face. Offline model, so it's our locally trained model. Okay, so we use 3 CNNs to train to learn the perturbation, 3 local CNNs with small, and we used UEP 200 images to learn that perturbation. Okay, so just a quickly turns out that for face recognition, remember, just note that this blue line is face detection. So it's hard. Turns out even after we add the perturbation, classifiers can know there is a face in the image. It's just that when you ask them to recognize the face, that's when our advantage is that at a beta value of 3, their detection face recognition accuracy is less than 20%. Right? It's typically 95 plus if it's a clean image, right? So it's pretty effective. Okay. But turns out there is an attack against UEP. Because I've learned the UEP such that I can add it to multiple images, so I don't have to learn one for every image. That turns out to be a downfall for this scheme, in the sense that if you added the same perturbation across multiple images, let's say I collected 10 images of you that you added a perturbation and posted, I can do something called a median estimation across these images, create this, an estimate of the perturbation. It's not the true perturbation, and try to reverse it. So you don't get a clear original image, recovered image as before, but it's good enough for a CNN to classify it. So the reason that we used one perturbation across multiple images is to keep it practical. We don't want to learn a perturbation for every image. We don't want end users have to spend so much computation to do that. But it turned out that also makes this scheme vulnerable. Right? So we went searching for better schemes. So then we looked at, previously what we looked at is a learning-based perturbation, where we actually learn using a CNN what this perturbation should be. Then we went to look at something called semantic adversarials. What are these? There is not much learning involved. Turns out, and this is a little bit of ad hoc too, even though there is some intuitive support for these things working. It's a little bit of ad hoc discovering these. It's still fairly recent, 2018. Turns out, for example, if you just change the color scheme or hues, right, transform the hues, CNNs can be fooled using these stuff, right? We don't know how long they will be, but they can be, okay, for now. Right? So there are a couple of schemes that came out showing that, okay, I don't need to learn a perturbation. I just, if I can add a certain hues, change the hues or add certain kind of things, we can, or angle of those images, then they can be fooled. But the one we focused on are called overlay images. So an overlay is a very simple idea. There's one image here of a person, here is image of a car, and you overlay them on each other using a weighted addition. Simple, right? So at 50%, you get both of them. Turns out you can use simple overlays to fool video captioning, right? So if you have a video, it's a series of frames. Every 30th frame or every 20th frame, if you introduce an overlay, a video captioning service can get fooled into thinking that there is a car here in this video, right? So this came out in 2017. We adapted here for our application, but you can't really use this for image privacy, turns out, because in signal processing there is a technique called blind signal separation, that if you have 3 input images and you give me a mix of each of these images, so this one is a mix of this person here in the car, this is a mix of, the second person in the car. If you just give me these mixed images without the originals, I'm able to recover, something close to the originals, right? That are recognizable at least by a CNN, right? They're not perfect. So blindly applying transparent overlay images is not going to work, especially if you want to use the same overlay, right? At the same time, using a single overlay for every image means I have to store those overlays. I might as well store my own images locally, right? So it's not practical either. So what we came up with, we call randomized transparent overlays. And what we try to do is that we try to generate a unique overlay for every image using only few overlay images and a secret key. So the storage cost is these few overlay images and one secret key. And we can generate a huge number of overlay images to be applied for a large image data set. So at a high level, let's say this is my set of overlay images, random images we picked. We didn't have any specific criteria, right? Let's say this is the image that I want to add the overlay to. So out of this, using this image ID and just something as inputs to pick, we pick 2 images out of this at random. This could be a larger set, right? And again, using this secret key, we divide these images into blocks and permute them, and then we add them to this target image. So this is basically, the idea is that using a small set of overlay images, you can generate a whole large space of unique overlays, right? This doesn't look that usable, that it's not that recognizable, but it turns out that if you pick the right parameters, so alpha is the weight of the overlay, weight of the original image. So as you increase alpha, you can see more of the face. As you decrease alpha, you see less of the face, right? And this is the block size of how many blocks we divide the image into. And this K, this is a different axis, is how many overlay images we add for the original image. As you can see, if you use too many overlay images, it's not very effective. You can easily recognize the face, humans and CNNs alike. But if you keep the overlay images that you add to be small, it does cause some fuzziness that sort of thwarts CNNs. So this is the sweet spot. Few overlay images, a small block size, okay? With that, we again evaluated our image overlay set is 30, and face scrub is the data set of celebrity images. Again, we evaluated against Google Vision API, Clarify, and our local model. And you can see face detection, just detecting there is a face, is actually, fairly, we can't stop that much. Alpha 0.4 is our sweet spot. So yeah, we are, and the block size less than 20. So yeah, we get, can you guys still hear me?
Yes.
Okay, sorry. My Zoom did something weird, so I wanted to check. So yeah, we do have a sweet spot, but it's not that effective. And anyway, Google Vision face detection is a little bit weaker than, for example, the other one seems to be. But it rapidly gets better at higher block sizes or higher alpha values, okay? Clarify face recognition and detection. So face detection, we can't turn out, Clarify can still tell there is a face. But face recognition, if you see for alpha 0.4, it's it's pretty good. It keeps the recognition less than 20%, even for higher block sizes, actually, and even for alpha values a little bit higher, 0.45. Okay, so it's pretty good at thwarting recognition. Same thing with the local model. Clarify is actually the best performing. We can keep the detection also low for deep face, for example. So I'm going to move ahead. So we said, okay, can this be attacked? Can unauthorized classifier somehow defend against our scheme or attack our scheme, right? So the first one we looked at is, okay, since the face looks fuzzy, can we smoothen it out? So we tried grayscaling, blurring, Gaussian filter smoothing, and median estimation and removal. And turns out that for face recognition, it still keeps recognition low. None of these simple filtering or smoothing techniques don't work. We said, okay, then let's just train the CNN on images that look like this. So we actually give KRTIO images to the CNN during the training. It's a little bit better, right? If for a CNN that was not originally trained on KRTIO, so we keep them, let's say, at less than 20%. Now it goes up to less than 40. So obviously, if you train the CNN on these images, they do better, but still, compared to 95 plus accuracy, they're still less than 40%. So it's pretty robust so far. The other thing is, you can't really train a CNN on KRTIO images. For large CNNs, it takes a lot of additional training time, right? So it is computationally expensive. And by just training on one kind of KRTIO, if you come up, variations of KRTIO, then you can't guarantee that it'll work against them. So we feel good about this for now. Again, it's a cat and a mouse game. CNNs are getting better. I'm sure providers will find better ways. So so far, this has been interesting work. So looking to the future, we are looking to evaluate the privacy provided by the thumbnail preserving encryption. So we evaluated security. We want some formal models to evaluate, formal guarantees for privacy. And also, we did a usability study. Can users browse TPE protected images? We also want to do a privacy study. Can users recognize, non-owners recognize the images, right? So we're working on that. The other thing that's caught our attention is super resolution techniques or face hallucination, or these are techniques. If you give them a low resolution image, they blow it up to a higher resolution. They're actually very effective on a 2x2, so they can blow up both dimensions by double, right? They're pretty effective at that right now, the current state of the art. So it's a threat against TPE. You can take a thumbnail and blow it up using super resolution and then give it to a machine learning model to recognize. So we are working for against super resolution based threats, and we are also exploring adversarial examples against super resolution. So this is some ongoing work. We hopefully will have something to talk about in the next 6 months or so. So that's all for the technical part of the talk. I think Alan already pitched, but I'm also passionate about education and outreach in this space. So we are starting with OSU and School of EECS support what's called Oregon Research and Teaching Security Operations Center. It's like a teaching hospital for security operations. If you all want to know more about this, please reach out to me or see how to get involved and support this effort. We also run cyber camps for high schoolers. Due to COVID, we didn't do it in summer. We are doing mini camps in fall and spring. But over the last few years since I've been involved, we've reached out to 150 plus students. Charlie is on the call. He's the founder who started this fantastic program, and we're trying to keep it going as he envisioned it. I also, in my copious spare time, do some robotics club for the local school. We couldn't do it this year because of COVID, but if any of you want to support these efforts, please reach out to me. Thank you.
All right. Well, thanks a lot. That was very interesting. So we have a little time for questions. I'm sure Rakesh can stay on longer. I have to leave at noon, but does anybody have any questions to get things started? So I see Jaspal has one. Do you want to just unmute and ask it, Jaspal?
Let me.
Sure. Yeah. Am I audible?
Yeah, I can hear you, Jaspal. Yeah.
Yeah. So I was curious if the trivial solution of just storing the thumbnail along with the encrypted image, is there any drawback to that other than
no?
Okay.
No. Yeah. So there's actually, we looked into it, and in the paper we talk about it, is that JPEG actually provides you a place to put a thumbnail, right? And you can encrypt the image and embed a thumbnail into the JPEG. But the challenge with that is, at the time, at least, all the platforms we've tested with, like Google Images or Photos, or all of them strip all metadata before storing it into their repository. So when you retrieve the image, all the metadata is lost. Second thing, looks like they actually compute the thumbnail using their own approach on the image provided. They don't. They will not give you the thumbnail that you included in the metadata, even if it keeps it. So without support from the providers, yeah, that's a very simple solution actually. Probably elegant if there is some support from the providers.
Yeah, that makes sense. Thank you. I had one more small question. Is the encryption scheme randomized or deterministic in your thumbnail preserving?
It is randomized. Yes, I didn't show the details. It is randomized, and Mike is our resident expert on that. So yeah, it is randomized. We actually give as part of the key, we give an ID that randomizes it, sort of acts as a salt.
Okay, thank you. Yeah, that's all I had. Thank you.
Yeah, thanks. Do we have any other questions from the audience? Yeah, I did have one, maybe higher level question. So who wins this game? From what you've seen, so we have these machine. I mean, I've sort of seen this area. It's just back and forth, and thousands of papers now on this attack, this defense. Yeah, I mean, I've got my opinions, but I'm interested to know what you think is going to happen here.
Yeah, so turns out that there are actually pretty good defenses against black box attacks, right? So if you have reasonably effective defenses against black box attacks. To my knowledge, there is no reasonable defense against white box attacks yet. Maybe in the last couple of years, maybe if something came that I missed. So doesn't seem to be a good defense against white box attacks. But I know that in the last few years, machine learning community has focused on more fundamental changes to these models, right? So I suspect that CNNs will get better at dealing with this, but I suspect there'll be other attacks that will emerge, right? So I suspect this cat and mouse game to go on for a while before we find equilibrium and say, okay, this is known weaknesses that we know we can't, patch in a CNN, and so there'll be some equilibrium. But for now, the game seems to be, the paper production in this topic has come down. We don't see so many attack and defenses paper as much anymore, right? They're now looking at more fundamental defenses than just system level defenses that we've seen so far. So I feel like that thing is already ending, but I think semantic adversarials is a new one. I don't know at what rate the semantic adversarials are being discovered yet, right? But I suspect it's also has a structural relation to the design of the CNN, right? So if once that is altered, then things might change, or people might be able to come up with CNN structures that are more resilient to these semantic adversarials. For example, I didn't get into this, but KRTIO leverages the fact that a convolution operation in a CNN is trying to learn from a small portion of the image first, right? And then you move the window and you learn. You move the window, you learn. We're trying to sort of, by adding all this noise at that level, we're trying to break that learning process. We're trying to break the continuity between pixels at that granularity, right? And that's what seems to be effective. That's why KRTIO seems to be effective. But if CNNs use a different structure or a different way of absorbing information from the image, then KRTIO probably would fail to be effective.
Thanks.
Yeah, I'm always curious to see what Fuxin, you and Tom would think about these schemes, and look at how these things may. I'm sure many of these attacks can be shut out by certain changes in the structure, but I suspect more other attacks might emerge then. Yeah.
Thanks. Any other questions? We have a few more minutes.
Yeah, I just had a quick question.
Sure, go ahead, please.
Yeah, so you just, Professor Rakesh, you just mentioned about the breaking the learning process of a CNN, where you realize that okay, CNNs try to learn the relation between pixels which are close by, and then the convolution window moves. But what if an image recognition system doesn't use convolution at all? Because there are new transformer-based image recognition papers. So how would that affect?
We've only tested, obviously. So CareTR is designed for the current convolution-based CNNs, right? Image recognition. It won't work against others.
Okay.
So there's a difference. If you look at TPE, it gives you some nice formal guarantees, right? About, okay, this is the information I'm leaking. Whatever you can learn from the leaked information, you can learn, right? Otherwise, whereas the second part of the talk is mostly empirical, right? I cannot give you guarantees on, against what CNNs this will be effective. So it's mostly empirical work, and that's less satisfying on this end. But it seems we wanted to document the existence of these kind of privacy measures. Yeah.
Okay. Yeah. Thank you.
Yeah, it will change if you have a different image recognition. Yeah.
Yeah. Okay.
I've got another question. This was, we mostly were talking about faces as the domain of interest. There's other interesting domains. If I'm automating shopping, I pick something off a shelf, or if I'm doing self-driving cars and I'm coming up to an intersection, those sorts of things. Maybe I don't need to recover the original image, but I would like to know that it's been polluted.
Yes.
So that I can raise a flag and take other action.
Yeah, definitely. Thanks, John. So we actually have the same student who did this adversarial-based image privacy student also did defense schemes against adversarials, and that's the goal. Where I don't need to classify an image if an adversarial is added, but just I need to know that it's been added. So I refuse to classify it. Right, for safety critical applications, that's the key. So we actually have some approaches in that direction as well. It's just that I felt it'll be too much to cover in one talk, but we've done that. Yeah. So one of the ways that we do, and I know, for example, Alan and Fuxin have schemes in that direction as well. One way we did that in our case is, especially out distribution, right? It's not just adversarials. Let's say you have a CNN trained to recognize cats. You give it a dog. Different types of cats, you give it a dog, it'll think it's a cat because it thinks that's all its job is, right? So what we try to do is that we try to learn the boundaries of these classes, and try to train the CNN to say, okay, if you go out of this boundary, say I don't know the answer.
Cool.
Right, for each class we call them protective. The sets we use to train the CNNs, we call them protective sets. Turns out there are many different sets that samples that we can use as protective sets. So one of our work is, how do you recognize a good protective set, right? So those are the kind of works. It's still, I'm not an expert in this space, so I tend to touch on the system level approaches and not the deep theoretical approaches into machine learning, which is what Alan and Fuxin focus on. They might have more satisfying solutions then, but we have some effective systems approaches to do this, for now. Any other questions? If you think of anything else that comes to your mind later, so you have my email address on the screen. Feel free to drop me a line. I'll be happy to answer your questions offline.